That's where you have to go.
Today's lecture, we will continue on example and impulse, step and round responses. And if we have time, we will go introduction to convolution. So, today's lecture, there should be the due date for homework number 3. So you already should submit homework 3. And the readings are on page 40 to 50. And Friday, the readings from page 40 to 50 as well. Next Monday, or in Monday, the due date for homework number 4. Okay? And Wednesday, the 7th, it is the due date for MATLAB project, MATLAB 2. And Kim also notice that in Wednesday, I will be out of town, so no live meetings. I have some news for you. So no live meeting. So I will see if I can have a pre-recorded lecture. I will let you know, I think by Monday. If I have a pre-recorded lecture, then you can watch on Canvas. Or if I cannot make it, then there will be no class. But keep in mind that in Wednesday, there's a deadline for MATLAB 2. Okay, so please make sure to go to Canvas and see what are these homeworks and projects. And also on Wednesday, there is a due date for homework number 5. But that homework, there is no submission. So don't worry about the submission, but I encourage you to try these problems because those are important for the first exam. Okay? Any question about this? So again, in Wednesday, the 7th, February 7th, there will be no live meetings. It might be pre-recorded lecture or there might be no lecture. Again, I will let you know by Monday. Let's continue in our example that's for to do this impulse response. Basically, we got to this conclusion, the time derivative, h of t e power t over tc, using the integrating factor method, equal 1 over tau c delta. Now, we want to get rid of the derivative, so let's do the integration. Do integration to remove the derivative. By doing the integration, I'm going to make the derivative from 0, negative. What do I mean by 0, negative? 0 left. The unit is up to t d by d tau, h of tau, e power tau over tau c, d tau. So you notice that I use the same tau instead of t to generate variables because I already used t in the integration factor, in the integration period. Then it will equal to 1 over tau c, the integral from 0 negative to t delta of tau d tau. So we call the time derivative du of t by dt equal delta of t. Therefore, delta of t or u of t as an integral between negative infinity to t delta tau d tau. So since tau here located at 0, centered at 0, so I will say it's not only from negative infinity to t, it can be also from 0 and negative to t delta of tau d tau. This is equal to u of t. Because our target is to include, when we do the integral, we need to include all of the error. So when I make 0 negative, I'm including all of the error. But if I made 0 alone, it will be indefinite. If 0 positive, I will not include. We call the limits in math. So this is 0 positive, 0 negative. Okay? So when I say at the 0 itself, I'm not including the arrow. If I make it from, for example, 0 negative or 0 positive. Therefore, it will be u of t. So as a result, let's continue the integration and substitute this integral as u of t. So the derivative will cancel the integral. The only remaining, or we will have h of tau. We will have h of tau e power t over tau c between 0 negative to t equals to 1 over tau c. The integral here is u of t. Now let's substitute 0. This yields to t and 0. Substitute t instead of tau t, it will be h of t e power t over tau c minus h of 0 e power 0 over tau c equals to 1 over tau c u of t. Our target is to find h of t. We know this factor equal to 1. So h of t will be 1 over tau c e power negative t over tau c plus h of 0 negative, before there's a negative, e power negative t. I forget to take it off one. E power negative t over tau c. Now, that's the overall function. That's the impulse response. And that's h of t, the output. Most likely, we used to assume capacitor starts uncharged. So this yields h of 0 negative, which is the same as the voltage of the capacitor, equal to 0. So this will yield to h of t equals to 1 over tau c e power negative over tau t over tau c, and forget u of t here, times u of t. So the response, if we need to plot it, we will start from t equals 0 because we have u of t. So here t equals 0. Then, since it's exponential, it will be at 1 times 1 over tau c, 1 over tau c. Then it's decaying because it's negative exponential. Okay? That's h of t. That's okay, does this make sense? So that's how we calculate the impulse response for this example, which is for the RC example. Now, let's try to do the step response. This is for the same example. Number 2. Same RC circuits, but we need to do step response. Step response means the input is u of t, the output will be y step. That's what we will do. Let's recall the differential equation. The differential equation was dy of t by dt plus 1 over tau c u of t equals 1 over tau c x of t. So let's replace to find the step response. So it will be dy step of t over dt plus 1 over tau c y step of t equal 1 over tau c u of t. Now, how to do this integration? We will apply the same things called integrating factor. So let's multiply both sides. Which is the same thing that we did in the previous lecture, but now I'm going to do it real quick. multiply both sides by e power t over tau c. This yields to be dy step of t over dt e power t over tau c plus 1 over tau c y step of t times e power t over tau c equals to 1 over tau c u of t e power t over tau c. And last lecture we already defined this thing. It is actually d by dt of y step of t e power t over tau c. You can recall last lecture, the last 10 minutes of last lecture, we already proved how to do this. Then this will equal to 1 over tau c u of t e power t over tau c. Now we need to remove the derivative. Let's apply the integral the same way that what we did before, which is do the integral to remove the derivative. Let's do the integral. So this will be the integral between 0 and from left to t d by dt y step of t e power tau over tau c, because we change the variables, d tau, replace every t of tau, so here y of tau actually. Then here d by d tau equals to the integral between 0 from left to t 1 over tau c u of tau e power tau over tau c d tau. Now, how to do the integral? So this is right hand side, this is left hand side. Let's do every side alone. So I'm going to start from left hand side, which is I think I mixed it. Here is my right, here is my left. Let's start from left hand side. The integral between 0, negative to t, d by d tau y step of tau e power tau over tau c d tau. The integral and tau will cancel each other. This will yield to y step of tau e power tau over tau c. Then substitute from 0 left to t and assume initial condition 0, so this will yield to y step of t e power t over tau c minus y step of 0 e power 0 negative over tau c. So assume 0 initial condition so this term equals 0. Therefore, the left hand side will equal to y step of t e power t over tau c. Okay? So now we're done with the first side. Let's go with the second side, which is right hand side. So right hand side we have a step input. So basically, let me rewrite it what it is. We need to calculate the integral from 0 to t 1 over tau c e power tau divided by tau c u of tau d tau. So we have different things which is depending on t. So we will say that if t larger than 0, so what we will have u of tau is actually 0 when tau is than 0 or 1 when tau is than 1. So if it is positive, then we are guaranteed u of t equal to 1. So here u of tau will equal to 1. So as a result, this will be the integration from 0 to t, 1 over tau c e power tau over tau c d tau, because u of t equal to 1. Then it will be as 1 over tau c is it here, 1 over tau c, then times, I think tau c because they will cancel each other. Integral terms. Okay, so we have the integral 1 over tau c, the integral between 0 to tau over tau c. Okay, so this will make it 1 over tau c, the integral between 0 from 0 to t equal tau over tau c d tau. Now we can do this thing, which is basically move tau c to this side. So it will be as an integral from 0 to t e power tau over tau c d tau over tau c. It looks like the integral from 0 to t e power, let's say, a, or I would say like x dx. This will be e power x, the integral from 0 to t. Or in other words, it will be as e power tau over tau c from 0 to tau c, which is going to be as from t, from 0 to t, e power t over tau c minus e power 0, which is going to be as e power t over tau c minus 1. Then that's the first thing. The second thing, when t less than 0, this yields u of tau equals 0. Because unit step when time is than 0, it will be 0. This yields to the integral of 1 over tau c e power tau over tau c times 0 d tau from 0 to tau. This will make the integral from 0 to t 0 d tau, which will make it 0. So as a result, we will say right hand side, it can be either e power t over tau, tau c minus 1 when t larger than 0, or 0 when t less than 0. What does this mean? This is the same as yes.
So how did you eliminate tau c from the interval?
Here, so I put tau c, it's dt, then dt over d tau c. That's what I did, you see? Then in this situation, I assume t over tau c as x. So here this will be x, this one is x, this one is x.
Oh, I see.
So it will be the integral of ex, e power x dx. Okay. This yields to e power t over tau c minus 1 when t larger than 0, or 0 when t less than 0. Okay? Now, how can I simplify it more? Because we know the step function. So we can say it is right hand side equal e power tau over tau c minus 1 times u of t. Are those the same? Yes. So that's how the right hand side. Then as a result, we will say the left hand side equals to right hand side, which is left hand side was e or y step of t e power t over tau c equals to right hand side was e power t over tau c minus 1 u of t. Now let's divide all the terms by e power t over tau c. So it will be y step of t equals to This will be 1. This will be 1 over 1 e power t of tau c, which will make it negative. E power negative t over tau c u of t. Then that's this. This is the step response for RC circuits. So you will realize that there's a lot of methods. You just like need to know what's u of t, what's delta t, and that's it. Any question? Yes.
Do we always assume that the initial condition when at 0 is going to be 0?
In this example, we assume it's 0. But if they are not, then like what we did, for example, here, we still need to write this one. So if there is no information at all about initial condition, then assume it's 0. The default is 0 unless something else mentioned. Any other question? Now, we did calculate two things, which is step response and impulse response. Well, I have a question. How can we do step and impulse to the circuits or to the RC circuits in real life? How can we do it in real life? I mean, how can we make step input in real life? Or how can we do impulse response in real life? Let's look at this circuit for assume this is plus minus 1 volt. This is a source, and here is a switch. Here is R, here is C, here is the outputs. So this is my system. So if we let the switch turn on at t equals 0, this means if you turn on the switch at t equals 0, turn on switch at t equals 0, this means you did u of t. Was 0 at t equals 0. If you make it at t equal tau, then it will be if on at t equal tau, then it will be u of t minus tau. Okay? That's how we do it in real life. Basically, turn on the switch, this is the step response. Turn off the switch, then this is the other step response. So before doing the action, everything was 0. When you turn on the switch, it will maintain on. Is this correct? That's how we do this in real life, which is how we do the step response. Then here, the input is u of t, the output will be y step of t. And even if we're doing the lab, on, off. Now, another thing, which is we did now step response. Here is the step. How about the impulse? Here is circuits. Here is R. Here is C. Then here is Y. So here is we have a switch. So most likely, we have position 1, position 2, and here is the source. Most likely, the switch will be on when t goes to 0. And at the same time, goes to 0 negative. We want it to go off at t equals 0 positive. In this situation, we guarantee that we have here as delta of t, then the output will be h of t. That's how we do the impulse. But the thing is, on at t equals 0 negative, then or position 1. Here's position 1. Position 2. So position 1 at t equals 0, position 2 at t equals 0, positive. That's how we can achieve or do the impulse response, or to do the impulse response. But the question is, are we able to do this? Can we do it? No one can do it actually. That's what it is. No one can do on and off at the same time. So because something happening instantaneously, and there is nothing in real life, which is something unrealistic. Okay. How can we achieve something closer to this? Is basically what's happening in real life. Here is the switch. Here is the position. Position 1, position 2. Usually it will take time, right? Usually it will take time to go from 1 to 2. So let's assume 1 at t equals 0, 2 at t equal epsilon, such that epsilon very small number. Very small number. So that's what we do. Basically, we have this small time because even if I let the machine do it, they cannot do it in fast way. I mean, if I do it by myself, it might take 1 or 2 seconds. If I make it by the machine, it might take half seconds. If I have a super machine or something working fast, then 1 millisecond. But you cannot reach 0, right? There is no way to move from here to here like this in 0 seconds. It will take time. So we have a small time to do this. So basically, the inputs x of t will be as u of t minus u of t minus epsilon. That's what's happening. So the input is not actually delta. It is combination of u of t. Now, if t or epsilon goes to 0, then x of t will goes to delta of t. So sometimes we will get, instead of 100% accurate delta of t, how about if we reduce as much as possible and get accuracy around 80%, maybe 95%. So that's the way. So let's here start to plot. I use MATLAB to plot when epsilon equal to 2 seconds. So this is the ideal impulse response if we have the impulse that's what's supposed to be. Here, if I do it, by myself, and I'm slow, so it takes me 2 seconds, here is how the response looks like. So you will see, you'll realize that at 2 seconds, it has similar performance, but it's not accurate, right? You see, look at the red and the blue. The blue donates for the ideal response, while the red, this is my response because I'm slow. It takes me 2 seconds to go from position 1 to position 2. Okay? Then you will see it's not really accurate, but at least the trend, overall trend, it goes up and goes down, but there are still some errors. And these errors sometimes, I not consider this acceptable, so it's not, this is not acceptable, so it's not considered as an error. It's not considered as a response. Now, how about if I do it faster, or take my colleague, I know he's fast, and do it switching faster than me, then he did it in 1 second. So when you do it in 1 second, you will see, again, the blue is the ideal, the red is the practical response. Here is the difference, that's what we see between theoretical and what we have in real life. As you will see later in the future, when you go to the practical, when you work with the industry or you work in research, you will realize the real world is different than what we are learning here. There are a lot of differences. So you will learn, okay, we've learned the ideal situation, but the other is not yet. So how can we deal with this? Then look at this. When we make epsilon low, when we move from 2 seconds to 1 second, we can achieve a better accuracy, right? it's better than 2 seconds. And very close to each other. So I would say this is maybe correct 40%, but it's still not acceptable. So if I bring a machine that can do it faster than me, so we did it by epsilon equal to 0.29, so very fast. Then, look at the response, how it looks like. Okay, they're close to each other. Let's do a zoom. By making a zoom, you will see they are very close. So even like, I would say like it is 90% accurate. Okay, I think 90% can be acceptable. That's how we do this in real life. So sometimes, I cannot make the theoretical 100% correct, but if I make it closer, that can be fine. Then I can make some error analysis to make sure if that error is very large or not, or is this acceptable or not. Then I can report this by this in my report. That's the error that I have. Then based on that, your boss can say, okay, this can be acceptable or this can be not, or look for some improvements. Okay? So again, to do the impulse response in real life, impossible. We cannot do it. But how we can achieve something close to it? By making it faster, as fast as you can. So we can make faster switches, faster things by doing similar techniques. But if we make it as fast or the period between position 1 to position 2 as low as possible, then we can get it with higher accuracy. Not the exact, but higher accuracy. Okay, let's again recall LTI response. When we have inputs, here outputs. So when you have delta of t, the output we call it h of t. When we have u of t, the output will be u step of t. When we have r of t as ramp response for LTI, we will have to y ramp of t. And also recall the relationship between the inputs. What do I mean by this? Whenever you have delta of t and u of t, what's the relationship between them? Delta of t equals the time derivative du of t by dt. Then u of t equal also to the time derivative r of t by dt. How about the integrals? U of t will be the integral from negative to t, negative infinity to t, delta tau d tau. Or we will say r of t, something similar. The integral from negative infinity to t, u of tau d tau. Okay, do you agree with me on this? We already learned this before, right? So what matters here in LTI system, something interesting. In LTI system, what's applied in inputs can be applied on outputs. That's something interesting. This means if we know the step response, we can find the impulse response or ramp response easily without doing all of the calculation. Likewise, so if I would say h of t equals the time derivative d by dt by u step of t. And I would say y step of t equals the time derivative d by dt y ramp of t. Or when we have y step of t, it will be the integral from negative infinity to t, h of tau d tau. And the same thing for y ramp of t equal negative infinity to t, y step of tau d tau. So as a result, if you find the impulse function alone, you can find the impulse, you can find the ramp, or you can find actually the ramp and the step in an easy way by doing the integrations. Or if you have the step, you can find the impulse by the differentiation, ramp by integration, and so on. Okay? Now, this can be again beneficial for us, so we don't need to do the calculations for every element. Okay, let's assume we have number 3 for RC circuits, because remember, number 1, RC circuit with impulse response, number 2, RC circuit with step response. Now let's go to number 3, RC circuits with ramp response. So I can use the integrating factor differential equation and do all of these techniques, or I can use this results. Recall, we have y step of t, that's what we calculated in step example number 2, equal 1 e power negative t over tau c u of t. That's what we do. Now we need to calculate the ramp response, so we can calculate it easy using that conclusion that we calculate, which is to be the integral from negative infinity to t, y of tau, y step of tau. I don't need to go back to the differential equation and do the integrating factor and do the other things, so I can make the life much easier. So it will be the integral from negative infinity to t, 1 e power negative tau over tau c, d tau. I just changed the variables. Oh, I forgot u of t. U of tau, d tau. Now we have different situation depending on if t larger than 0 or if t less than 0. If t less than 0, u of tau equal to 0. So what will happen? It will be an integration from negative infinity to t 0, d tau, which will make it 0. Case number 2, if t larger than 0, then u of tau will be 1. Now I'm ready to do the integration. So it will be the integral from negative infinity to t, 1 e power negative tau over tau c, u of tau, d tau. Now I need to do this integral. How to do this integral? Actually, we know in the integral from negative infinity to t equals to negative infinity to 0 plus from 0 to t. But here I forgot to mention it's equal to 1 if t larger than 0. So what will I do? Basically, this will be as integral from negative infinity to 0, 1 e power negative tau over tau c, u of t, d tau, u of tau, d tau, plus the integral from 0 to t, 1 e power negative tau over tau c, u of tau, d tau. Now, since the integral from negative infinity to 0, this is outside of the brackets for u of t, because we know u of t, u of tau will be from larger than 0. So, this will be 0. While with these terms, here, less than 0, larger than 0, this will make it equals to 1. So as a result, this term will be 0, will cancel each other. The only term remains, which is the integral from 0 to tau, t, 1 e power negative tau over tau c, d tau. Okay? Now, how to do this integral? Basically, it will be let's multiply by tau c over tau c. So this will make it tau c, the integral from 0 to t, 1 e power negative t over tau c, d tau over tau c. So this will make it like tau c, the integral from 0 to t, 1 e power negative x dx. So the answer will be tau c, the integral will be, here is x between 0 to t, minus e power negative x between 0 to t, Then let's substitute x as t over tau c. This will make it as tau c over tau between 0 to t minus e power negative tau over tau c. This tau over tau c between 0 to t. Then close the brackets. I'm going to put the brackets in different colors so to avoid the confusion. Substitute them. This will make it to be tau c times t over tau c minus 0. Then here e power negative t over tau c minus e power 0 over tau c. Here between brackets. And before we the original brackets here. So as a result, this will make tau c t over tau c minus e power negative t over tau c minus 1. Let's multiply by tau c. This yields to be tau c and tau c will cancel each other. Will be t minus tau c 1 minus t over tau c. Or actually plus tau c e power negative t over tau c minus 1. So the overall answer y ram I think when we do the integral, because it's negative x, it should be positive. So just please make sure you both integral terms positive. Now, y ram of t equals to 0 when t less than 0, or t plus tau c e power negative t over tau c minus 1 when t larger than 0. And again, this is something similar to u of t. We can replace it by u of t because it's 0 when t less than 0, or that factor when t larger than 1. So this will be the final representation. Will be t plus tau c e power negative t over tau c minus 1, all of it times u of t. And that's it. Okay? Validate my answer. Try to find the y step of t, which will be d by dt of y ram of t. So this will yield to be derivative of t will be 1, then of the exponential it will yield to 1 e or negative t over tau c u of t. Or when you do y impulse, which is h of t, will be d by dt y step of t. This yields, I think it should be, you can test it. This is here, so this yields to be 1 over tau c equal negative t over tau c u of t. So if we know one of them, we can find the others by either doing the integral or the other analysis. Okay? Any question? Now we have a question. Here, for RC circuits, system RC circuits, it's simple system, and it takes me almost 2 lectures to discuss impulse response, step response, and ramp response. How about other inputs? How about if we have multiple inputs like, or other than that? So how about other inputs? For example, let's assume we have this input. Here is 0, here is 2, here is 4, and here is t. This input. Okay, what should I do? How can I deal with this? So the first step, write, this is x of t. X of t in terms of these three inputs. Delta of t, u of t, r of t. So in this situation, this equation will look like x of t will be negative 2 r of t plus 4 r of t minus 2 minus 2 r of t minus 4. That's how after making multiplications, you can do it at home, so it will be like this. Second step, compute response with respect to x of t. So we will say y of t will be negative 2 y ram of t plus 4 y ram of t minus 2 minus 2 y ram of t minus 4. Now, in RC circuit example, we already have y ram. So we have y ram as equal to t plus tc e power negative t over tau c minus 1 u of t. Now, we can substitute this here. But we will substitute h1 with respect to its value. So y of t will be negative 2 t plus tau c e power negative t over tau c minus 1. Then plus the second one, 4 y ram of t minus 2. So it will do the same y ram, but we will make this of t minus 2 plus tau c e power negative t minus 2 over tau c minus 1 times u of t minus 2. Just the same thing, but we'll put u of t minus 2. So this is plus. Then the last term, which is negative 2, then we have t minus 4. So just replace t by t minus 4 plus tau c equal negative t minus 4 over tau c minus 1 over t minus 4. Okay? So that's how we do it. Again, this is still for RC example. Another question. How to compute response to any input signal? Basically, we have x of t, LTI system here, then we have y of t. Now for any inputs, how can I do this? I mean, for impulse response takes a lot of time, step response, and for this function, okay, I can do it as r of t or delta of t, otherwise. Some other functions I cannot. Like if you have, for example, sine wave, cosine wave, whatever, I cannot do it. What should I do? The answer, we will use another method that's more generic and can be used for anything. It's called convolution. So convolution is the answer, which is we can do anything, any inputs, in a much easier way. Actually, there's also convolution something very important, so we can apply it a lot in many applications, many signals. So this is, that's it. We will stop here today. And next lecture we will go to the convolution.